Hello, I'm Mr. McBrien. This is TEJ3M Resistors. So let's start with a little bit of a question. When we're building our circuits, how do we direct current through specific parts of what we're building? How do we adapt voltages to suit specific situations? And how do we protect sensitive electronic components from excessive current? Well, the answer to all of this is the same. The answer is resistors. So, with what we're going to talk about today, let's summarize a few basic concepts before we begin. As was hinted in the introduction, resistors can limit current, they can divide voltage, and in some cases we can use them as heat generation systems, and we'll talk a bit more about that in a few minutes. They come in two main categories, arguably, fixed and variable, and they have various compositions. They're designed to exhibit specific behavior, but there are a number of different materials that can produce this. So they can be carbon or carbon film, they can be metal film, they can be wire wound. Okay, all of that's moderately interesting, but we have a number of other things to talk about with regards to resistors. When we're building them, and you've already seen these, when we're building our circuits, the resistors will typically look something like this. We will talk more about what those bands mean in a few seconds. Resistors, though, are a lot more than simply little components. A resistor is really anything that reduces the flow of electrons in a circuit. But when it comes to these little components, we can talk about how we determine what kind of resistor we have based on the color codes that are shown around the system. So 3 and 4 band color code is used for these we can say imprecise resistors, the ones that are plus or minus 5, 10, or even 20%. We call them 5%, 10% tolerance resistors. And for these ones, the first 3 bands are used to denote the rated value. The 4th band gives us the tolerance, how much the device may vary from the rated value. Now, when we go to interpret them, the first band is the first digit of the resistance value, the second band is the second digit, and the third band is something different. It's actually a multiplier, a number of zeros after those first 2 digits. We'll illustrate this more in a second. The 4th band, set off on its own, indicates the tolerance. So how accurate that number can be expected to be. Alright, this hopefully will illustrate better what I was talking about in the previous slide. So in a 4-band resistor, the first band is the first significant value. In this case, green gives the value 5. The second is the second significant value. In this case, blue, which gives us the value 6. And the third band is a multiplying factor. Red gives us a 100 value. And so now we have our value of our resistance, 5600 or 5600 ohms. Now, the band that's set apart, in this case gold, gives us the tolerance. And so we can say that this resistance is 5600 plus or minus 5%. And this number is important because we can then calculate what the minimum value a resistor that looks like this is liable to give us, which is 95% of 5600, or a maximum value, which is 105% of that value. And so we can calculate that, and if that amount of resistance variance is an issue, then we have to go and get a more accurate component. And that, of course, would be a precision resistor. These have much tighter tolerances, 2%, 1%, 0.5, 0.25, or even 0.1%. And they may have more bands. The reason why is because since we know them with so much more precision, we need to be able to communicate them with more precision as well. So the first 3 bands will indicate the resistance value. The 4th band instead of the 3rd is the multiplier, and the 5th band then indicates the tolerance. So the process we're talking about is really no different. Okay, so the 5-band code is on the bottom, and we can see the green, brown, black, and red on the bottom. And then, of course, brown indicates plus or minus 1%. So this is a 51,000 ohm resistor on the bottom in blue. 51,000, and it's plus or minus just 1%. Okay, but I'd invite you to pause the movie for a second and think about it. If someone hands you a resistor, are there other ways you could know what the resistance is? So think about that for a second. Are there any other ways? And the answer, of course, is yes. Now, for starters, you could look it up. We're used to the internet. Well, there are resistor color code calculators online. So if you have the time and a computer handy, you can quickly go and do a calculation to make sure that you're correct. But there's another option, and this is the one probably most typically used in TEJ. We simply measure it. So it's pretty fast to go and measure the resistance of your resistor and confirm it's the one you want. Now, there are other kinds of resistors besides those simple 4- and 5-band resistors. So surface mount resistors they look a little bit like an integrated circuit, and instead of using color bands, they have a little more real estate on them, and so they typically use alphanumeric labeling. And they'll use 2 or 3 digits, where R indicates that the value is in ohms, K is in kilo ohms, and M is in mega ohms. So the position of it as well will indicate the decimal point position. So they'll look like this. So on the left we see a 22 ohm resistor. In the center, notice that the M is in between the 2 digits. So this is a 2.2 mega ohm resistor, and this is a 220 kilo ohm resistor. We won't see many of these in our class, and so you won't be tested on this point. Now, sometimes we'll have situations where we want to be able to change the resistance of our circuit without having to rewire it. For this, we'll use variable resistors. 2 main components. We'll use one of them in our class, and probably you won't see the other. So a potentiometer is a 3-terminal variable resistor used to divide voltage, and it works very much just like a volume control. So you can turn the resistance up or down with a simple dial. And there's a number of circuits that we build in TEJ that can use that. On the other hand, a rheostat is one that's used to control current, and we typically don't play with those in TEJ. Okay, and here's the symbols for these in our circuit. Yeah, it's typically we'll use the potentiometer more than anything else. Now, resistors and power, it's worth noting that a resistor resists the flow of current, as we've talked about before. Well, sometimes circuits have a great deal of current. And when this happens, remember our power equation, P equals IV. And so when the currents are high, the power is proportional to current, and therefore the power goes up greatly. When this happens, our resistors will absorb a lot of power, will use up a lot of power, and as we recall, the first law of thermodynamics, energy can't be created or destroyed. The power that it consumes is converted into heat. And so resistors designed for high currents have to have a physically large surface so they can dissipate heat into the environment. And they can become quite hot. They'll heat the air around the device, and it's worth noting that a resistor, in essence, is a heater. Okay, so here's some examples of some power resistors. We won't use any of these in TEJ because we don't want to see large amounts of current. Okay, power ratings. We don't really need to talk about this too much. The power rating is determined by the physical composition, size, and shape of the resistor. It has nothing to do with the resistance of the resistor, only to do with the amount of power it can dissipate. And one thing you can note is the packages we have for our resistors, they do give us a wattage value for our resistors. And the wattage values are typically very, very low. And if you want to, you could do a quick calculation, and who knows, I might put that on a test, a calculation about what kind of current a resistor can handle based on its power rating. Or I might say how much voltage it could handle, and you'd have to calculate the maximum wattage it could handle and go from there. And it's worth noting that if you don't want your resistor to burn out, you should have you should not really get close to its power rating. Okay, resistors get bigger as they handle more heat. We talked about that with their surface area. One of the things that is inconvenient about resistors is that, unfortunately, as a resistor gets hotter, its resistance goes up, and so we have to accept that there's some variability in our resistors as they get warmer. And this also means, of course, that we don't want to get close to its maximum power rating. Okay, a little bit about combining resistors. So we've studied in science class previously the idea of resistors in series and parallel, so we're not going to belabor this point here. There's a worksheet for you to practice these things. Resistors can be combined in series and parallel, and the difference is very important. You need to be able to understand what happens there. So when we put resistors in series, they combine to resist the flow of current. So they act together to resist electron flow, and we simply add their resistances up. The effective resistance is equal to the sum of the resistance of the individual resistors. Very straightforward. And there's a little bit more math involved when they're in parallel. When we put resistors in parallel, we give additional paths for the current to take, and the resistance goes down. And so 1 over the effective resistance is equal to 1 over R1 plus 1 over R2, etc. Okay. And you've done these things before, so this shouldn't be too much of a challenge. So for your homework,